Hello, so welcome back to another day of Advent of Code. This is day 16. So I'm in a new location now, and unfortunately, I am unable to stream from here, and so all of these will be uploaded later in the day. But I'm hoping to still have a lot of fun doing these challenges, so we're going to move on to day 16 today. Let's get started. So, day 16. Packet decoder. By the way, yesterday's challenge was really hard, and I'm really hoping that today's one isn't going to be as hard as yesterday's. So, packet decoder. As you leave the cave and reach open waters, oh great, we got out of the cave. You receive a transmission from the elves back on the ship. Your transmission was sent using the buoyancy interchange transmission system, BITS, of course, a method of packing numeric expressions into a binary sequence. Okay, this feels a bit more my speed. Your submarine's computer has saved the transmission in hexadecimal, my input. The first step of decoding message is to convert the hexadecimal representation into binary. Each character of hexadecimal corresponds to 4 bits of binary, and that looks like the normal mapping, which is fine. The bits transmission contains a single packet at its outermost layer, which itself contains many other packets. Okay, this is completely, totally my speed, and I'm loving this sort of question. The hexadecimal representation of this packet might encode a few extra zeros at the end. These are not part of the transmission and should be ignored. Okay, so there are padded zeros at the end. Each packet begins with a standard header. The first 3 bits encode the packet version. The next 3 bits encode the packet type ID. These 2 values are numbers, version and type. Okay, all numbers encoded in any packet are represented as binary, with the most significant bit first. Most significant bit first means, okay, it's just left to right, good. For example, a version encoded as the binary sequence 100 represents the number 4. Packets with type ID 4 represent a literal value. Literal value packets encode a single binary number. To do this, the binary number is padded with leading zeros until its length is a multiple padded with leading zeros, until its length is a multiple of 4 bits, and then it is broken into groups of 4 bits. Each group is prefixed by a 1 bit, except the last group, which is prefixed by a 0 bit. These groups of 5 bits are immediately followed by the packet header. For example, the hexadecimal string D2FE28 becomes this. Below each bit is a label indicating its purpose, right? V is the version, T is the type, yep, and then ABC, and then like it says, the 1 means that this is not the final kind of set of values here. This one also means it's not, and then the 0 means it is. And so the number is 0111 1110 0101, which it should tell me at some point here it is 2021 in decimal. Every other type of packet, any packet with type ID other than 4, represents an operator that performs some calculation on 1 or more sub-packets contained within. Right now, the specific operations aren't important. Focus on parsing the hierarchy of sub-packets. Okay, an operator packet, there's so much information in this one. An operator packet contains 1 or more packets. Okay? To indicate which subsequent binary data represents its subpackets, an operator packet can use one of 2 modes indicated by the bit immediately after the packet header. This is called the length type ID. If the length type ID is 0, then the next 15 bits are a number that represents the total length in bits of the sub-packets contained in this packet. If the length ID is 1, then the next 11 bits are a number that represents the number of sub-packets immediately, or the number of sub-packets immediately contained by this packet. Okay, so that's quite different. 1 represents the number of sub-packets, whereas 0 represents the length of the packets. Finally, after the length type ID bit and the 15 or 11 bit field, the subpackets appear. For example, here's an operator packet with length type ID 0 that contains 2 sub-packets. Version type, length type, and then the length value, which is going to be 15 bits, yep, which is 27. The 11 bits labeled A contain the first sub-packet, a literal value representing the number 10. Now, is that because this is version 6, sub ID 4, and then it starts at 0, so it's 1010. Now remember, these are 0 padded at the end, or are they? No, numbers are 0 padded to the front. Yes, numbers are 0 padded to the front, so this is actually 10. Then here we have a packet. I'm just trying to read this without looking at my screen. 2 type ID 4, so this is a number. Type 6. Right, we don't care about that. Type ID 4. 1, so this is 0001, and then 0, so this is 0100, which is going to be 10100, which is 16 plus 4 is 20. Yes, it's 20. Boom, nice. After reading 11 and 16 bits of subpacket data, the total length indicated is reached, so parsing of this packet stops. As another example, here's an operator packet with length type ID1 that contains 3 sub-packets because the length is 3. Good. So we have another 4, and this is the number 1. We have another 4, and this is the number 2. And we have another 4, and this is the number 3. Good, 1, 2, 3. After reading 3 complete subpackets, the number of subpackets indicated is reached, so parsing of this packet stops. For now, parse the hierarchy of packets through the message transmission and add up all the version numbers. Here are a few more examples of hexadecimal encoded transmissions. I'm just going to take a look. Do we have, is this one packet? This is one packet, right? I'm just going to do a little resizing. Okay, good. This is one packet. This represents an operator packet, version 4, which just contains an operator packet version 1, which contains an operator packet version 5, which contains a literal value 6. This packet has a version sum of 16. Okay, so this sort of parsing is my bread and butter. It's the kind of thing that I do really well. I'm just thinking, how do we read bits out of, what's the easiest way to read bits out of it in Go? Because these are big Indian numbers. It might be easiest. The first thing that comes to mind is that I'm going to use a number to keep track of my position within a packet, and then I'm going to do a translation layer, which will basically, if I tell it to read, I'll basically tell it which bit to start reading from and how many bits to read, and given a long hexadecimal string, it will figure out where it needs to read from. Yeah, okay, so we'll do it that way. And we will start with, we have a, whoa, it's not what I want. Oh, by the way, yes, my program did finish at the end of yesterday's challenge, and I got a number. It finished about 30 minutes after I stopped my stream, but I got a number, I put it in, and it was right. So, yeah, sometimes you can brute force it if you're not press for time. Okay, so I just want something that I can use to test read this sort of thing. Okay, so we're going to say read bits. Start pos is going to be an int. Bit count, I'll just call it count, which is also an int. And we will return an int from that. Data is going to be an array of int. So it's an array of ints, and I'm gonna, in this case, I'm gonna say that these ints are, well, actually, no, it's gonna be an array of bytes, isn't it? Yeah. So start pos 0 to 7 needs to read the first index, 8 to 15 reads the second index, so it's divided by 8. So index is going to be start pos divided by 8. Now, if I'm reading oh, there must be a better way to do this. There must be a better way to do this. I need to make this N64 here anyway. So we're assuming the number is bigger than an N64. See, I'm not sure when it says you stop reading the packet. Honestly, I wonder if it'll be easier if we just read all the data. Might be easier if we just read all the data as bits. In fact, that is what I'm going to do. This is not the most efficient way to do this, but I'm going to store the data in memory as bits, as just ones or zeros. So I need I'm just going to pretend I have that. Because then I don't need to do any of this. I can just say data from start pos to start pos plus count. What we're going to do is we're going to have in N64 is an out. So all you do is you say out bit shift by 1 up. No, yes, and then out or equals B. Return out. So that would build that number into a thing. So just as an example of how this works, we can do this with the first one. How's this kind of go data? We'll call it bits, is going to be a byte array of these numbers. So I'm just going to do a little macro like this. Cool. So for example, if I say read bits, start from 0, read 3, I should get the number 6, which was the version number, right? Is 6. And then the next number I read, which is the next 3 bits starting from 3. It should be the number 4. Great. Then we need to know how to read the complicated stuff. We start from 6, we read 5. It's going to be 23, but it's not actually 23. It's 23 minus 6, and so on. Yeah, I'm happy with that. So we're actually going to convert the data into just a byte array of 1s and 0s, which will just make it a lot easier to read the data. We don't have to do all this bit like divide by 8 and mod and all the stuff, which just gets all into your head really quickly. Now I need to build higher level functions. I need a function to read a number, right? Because numbers are formatted in a very specific way. Read number. So a number just needs a start pause because the length of the number is encoded within the numbers. And what we do is we do this, and we say, okay, we read bits. We want to read 5 bits from start pause from the data. So part equals that. If part the first bit, so if part and 10, I believe, the 5th bit, yes, the 5th bit, greater than 0, then keep looping. But before we keep looping, what we want to do is we want to say out bit shift up by 4 or equals the final 4 bits, right? The final 4 bits. So that's 0f of the part we read, like this. And that will need to turn into an int. If it's greater than 0, we keep looping. So let's do it another way. If it is 0, we break. So we do this. Otherwise, we start pause plus equals 5 to read the next set of numbers. Return out. So we'll give this a go. Read number from my bits, and we're going to use the same input data, and this time we start from 6. Start from 6, and we should get 2021. Okay, we got some mismatched types going on. Part and 64 and int. Wow, okay. Oh, right, no, yeah. 2021, which is exactly what we want to read. So that's great. We've got that. So now we can build an even higher level function, read a literal packet. I hope that makes sense, right? I hope that makes sense. This sort of thing we always build up from the bottom up. So we build up little helper functions all the way. So this read bits function, I was going to write it as a to parse the hexadecimal values. Now we could do that, but it would take me about half an hour to actually code that up. And so I decided to take a shortcut and just store the data as 0s and 1s. So I need a function to decode into that. That's not very efficient, but that's a lot easier to write than all this arithmetic, bit level arithmetic. And so that's why I'm doing that. Once I have that bits function, I can now build a higher level function to read a number based on the algorithm that they describe in the code, how you check the top bit, and if it's 1, you keep going, and if it's 0, then you break, right? If it's 0, it's the last group, so then you break, and so on. So now I can read numbers. So next level is to read these entire literal packets. And we can build up a little type here that we can use to help with it, right? Type literal is a struct, and it's got a version number, which is int. It's got a, oh, actually, no, it's not. Yeah, no, it is. Type ID is always 4, which we know, so we don't actually have to keep track of that. But maybe I'll just put it in there anyway. And then value is an int64. Cool. So func read literal data from a start pause. This will return a, we'll just return a literal like this. That's okay. Okay, cool. So to do this, first we read. Oh, you know what we also need to do is we need to know how far we've read. Ah, yes. So this is why all the reader writer functions return this count. Because we need to know how far we are in the array. We need to know how much to kind of push the next value out by. So in fact, we could probably implement something with a reader interface here if we really wanted to. Read bits, we have a count, so we know the count, but I'll just check it in here anyway. So of course we return out count here. Here we return start pause plus 5, count plus equals 5, return count. This can't be count here. Yeah, but that's okay. And of course, these values are variables are now declared in the signature. There'll still be a 0 value, which is 0. Count plus equals 5. Return count. Great. So here, we first go. I guess we need a literal, so I'll just call L. L.version. In equals read bits data start pause 3. We'll say in equals start pause. In equals start pause. In plus equals count. So I'm just doing this because then it's there are multiple ways to do this, but I like to write it out like this so then I'm not losing track of what's happening. We can say L dot type ID equals read the next 3 bits from in, right? So then my functions always look the same. In plus equals count. Good. Then I'll say L dot value count is read bits, read number this time. Data in plus equals count. Return L in minus start pause, which is how far we've gone in our array. So here I should technically be able to go read literal. Okay, I can't mix these. Just call it C. Cool. It's going to complain about the same thing here. Undefined count. Right. Cool. I'm just going to make all these int64s to make them work. And I am returning 1 value instead of 2. Yeah. We'll just ignore it. And there we go. we're reading a literal. It was 6/4/2021, like it said, right? 6/4/2021, and it was 16 bits long, which is wrong because wait. Oh, this count plus plus has to be here. In fact, we can just chuckle this up here. In which case, I can say, no, this is right. 21, is it? Yeah, 15 plus 6 is 21. Okay. Now we have to be able to read. Okay, so I can't actually call it read literal. I have to call it read packet. So it's similar things. It's got this, but it's also got length ID. It's also got length. And then it's got sub packets. Go's not great for these sorts of things, is it? It's fine. I just do it interface. I think any is a keyword. No? Okay. I thought I read that yesterday. Maybe it's only in a newer version of Go. It is. It is in a newer version of Go. Which is a little bit of a shame that I have to have interface in here. So we read that, and then we switch on l.type ID. It can't be l dot anymore because we don't create the packet until later. Case type ID 4. It is a literal, and we go var l. Well, I guess we can just value is that, n plus that, return literal of version, type ID, value, default to something else. Oops. Default return nil, 0. Cool, so we're still getting the right thing out of the first one, good. But now we need to implement these other ones. If it's not, we do this other thing where we first read length ID is going to be read 1 bit. And then, man, so many ifs. If n is 0, which is the current case, we read 15 bits. Cool, and then read that many bits of data. I'm going to get back to that because this is the easier case to do. Yeah, let's skip to this one here first. This is the easier case to do. Length is 11 bits, I believe. Yeah, 11 bits, and then we just read that many more packets. For I 0, I less than length, I plus plus. We'll fill this in first, actually. Op is going to be an operator which has all these values. Length is length. And then packets, we will initialize. We'll keep it as null. Let's see. Op.packets plus plus equals append op.packets read packet. Okay, so we need to just write this out fully, just like one of these things. Is a read packet data in plus equals count. Yep, packets plus equals packet, and that looks good. We return op and in minus start pause like before. Length declared but not used on line 67. Right, of course. Just gonna comment that out. Now we're gonna come here, copy this test data into here. How long is that? 56. Just run that macro that I saved earlier. Did we read it? Version 7, version 3, length 1, 3 packets, the first packet. Version 2, 4.1, yep, version 4, 4.2, version 1, 4.3. So that looks good. That looks very good. Now the other one is just the one that's slightly trickier, but I think we can still do it the same way. So length is going to be that. I still need this, pretty much. Don't see why I wouldn't need the same thing. But if so, you could probably tie that up a little bit. But here, instead of this, we want to say while it's the length from here on out, right? Okay, so sub packet start is going to be whatever the in value is now, while sub packet start is less than length. If in equals 0, what? If length ID equals 0, what am I doing? Glad I caught that one. Sub packet start is in. Well, that is less than length. We do this and sub. Oh, the sub packet start is in. While in minus sub packet start is less than length. There we go. N plus equals count. Cool. I think, yeah, let's give it a go. I think that's okay. This is the one with 15-bit number. I mean, if it doesn't crash, that means this is good. 56 again. Oops. What I'm doing here is using what's called a macro in Vim. So earlier I saved adding a comma as a macro, and now I can basically use @a to insert a comma. And I'm just typing, you can kind of see in my screen over here what I'm typing, 55 @ and then if I type A, it's going to execute my A macro 55 times, which is adding 55 commas. And that's how I'm getting all those commas added in really quickly. I have a syntax error on line 81, apparently. Missing open bracket. Invalid operation. In minus sub packet start. Because in is an int. Yeah. So I'm just gonna do this. No, so it didn't crash, which is good. And it read, let's see, 1, 6, 27, which is good. 6 for 10, 2 for 20, 49. That's great. Cool. A few more examples. Okay, so now I have to write the converting hex into a byte array. So func hex to byte array, or to bit array, let's call it. Should we do a hex string? Oh, it's just a string. No, it's just a string. And we get out a byte array. So the byte array is going to be let's see, 4 times longer than the string, because each character in the string represents 4 bits. And I'm going to write it out, I think. For each character in the string, we'll write it out. Let's write it out. Case 0 out equals, oh, right. Let's do a length 0 but capacity that, so I can use append. I think I can write that. Cool. Yeah, it's not complaining about syntax error, which means it's good. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So 1, 2, 3, 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, and we just append the right things. Again, is this the most efficient way? You could probably come up with an algorithm. Oh, I really should have typed these up before I copied them. Whatever. Actually, I can do this, which is kind of neat. Okay, you can skip lines with vertical visuals, which means a little less work. And just going back up and getting all these ones in. So yeah, is this the most efficient way? No, but does it work? Yes. And it's quite clear what it does as well, which I think is helpful for us right now. So we can check this by, for example, taking the string And oops. Bits declared but not used on line 21. Of course it is. Is that string? No, because that's not the right string. We were looking at this one. Zero, zero, one, 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 zero, and a lot of zeros. It finishes with 1, 0, 1, 1, 0, 0, 1, and then a whole bunch of zeros. Okay, so I like that. That translation function looks fine. We'll test the translation function works by saying read packet that from 0. We should be getting the exact same thing we had before. So that's perfect. So let's just run it through some of these examples here. It contains an operator packet version 4, which contains an operator packet version 1, which contains an operator packet version 5, which contains a literal value 6. Okay, that's great. So we also want packet sum. So I'm just gonna split this up like this. Packet is going to be this, and then sum is going to be some versions of packet, which we will need to write. Some versions. This is going to be a packet, which is an interface. I'll be in 64 because that's the type of the versions. So we can switch p dot type case, I think, literal. Now how do I, okay, I need to look up the syntax for that. Hang on. Type switch Golang. I'm doing this off camera. Sorry about that. I'm just right. Sorry, I did that off camera just because I didn't want to get my search into my history. So the way you do this is you say fish p equals packet.type, case literal, we handle that, case operator, we handle that, return sum, and then here it's just sum plus equals p dot version, sum plus equals p dot version. If you had a language that had classes or inheritance, you wouldn't have to do this. Read packet returns 2 values. Yes, it does. We don't care about the second value. 4. We got 4 as the summed version because we need to keep doing this. If it's an operator, plus equals version, sum plus equals sum versions, p. So there's some looping going on. Oh, right. Whoops. For p2 in p dot packets, this, because otherwise we stack overflow. 16. That is the first answer. And yeah, the way I'm doing this, I'm probably going to implement the second half. I've probably implemented the second half already. This packet has sum of 12. This has a different ID and it should be 23. It is 23. This should be 31. It is 31. So I'm just going to print line length of my data, which should be 1 because it's a single line. It's not happy with all these unused variables. It is indeed 1. That first number is misleading. Now I think I actually have a function here called string. Oh, I don't have a function called string. Okay. Cool. So here, instead of that, we have data 0. That is my summed versions, 895. Great. Let's move on to the second part, which should be super quick because I have the entire thing parsed already. Let me just print out what my packet looks like. In fact, maybe I can do it like this, and it will print a bit more information. And you can see, it's hard to read, but you can kind of see all the names and things in there. Let's not do that because it's too hard to read. It's too verbose. Here you can see that this is the decoded version of my input, which is this. So now that I have the structure of my transmission decoded, you can calculate the value of the expressions it represents. Great. Packets with type, so 4 are literal values and everything else is different. So let's see, type IV0 are sum packets. Their value is the sum of the values of their subpackets. If they only have a single subpacket, that is the value. Packets with ID type 1 are product packets. Their value is the result of multiplying numbers together. If they only have one subpacket, their value is the value of the subpacket. Great. Packets with type ID 2 are minimum packets. Their value is the minimum. 3 is maximum. 5 is greater than packets. Their value is 1 if the value of the first subpacket is greater than the value of the second subpacket. These packets always have exactly 2 subpackets. And then this is less than 1 and 0 and always have 2. Packets type ID 7 are equal to packets. It's 1 or 0 if they have, and these ones always have exactly 2 subpackets. Using these rules, you can now work out the value of the outermost packet. What do you get if you evaluate the expression, which is exactly what I expected it to be? In fact, this is looking a little bit lispy. Cool. I mean, I expected it to be this, exactly this. So we just need an eval function, really. So we do the same thing as our sum version, but slightly something a little bit different. Var out, let's go in 64. Switch type. If it's literal, out equals p dot value. Actually, we don't need out, just need return, because that's what it is. But if it's an operator packet, then we now need to take into account what that value is. So we switch p dot type ID. We'll start with the easy ones. Yeah, we'll start with the easy ones. We'll start right at the bottom, case 7. If it is 7 equal to, then we know that there has exactly 2 subpackets. It's a given. We say p dot packets 0, and we need to eval that. v1 is this. v2 is going to eval p dot packets 1. If v1 equals v2, return 1. Else, return 0. Cool. It's not going to compile for a while. That's okay. So that's easy case 1. Going to do 5 and 6 as well, which is the exact same thing except with 5 if, okay, let's just read this carefully. If the value of the first packet is greater than the value of the second packet, it's 1. So first packet v1 is greater than v2, which means this is v1 is less than v2. Cool. So we have 3, 2, and 1. These should be relatively easy to do as well. We'll start right from 0. Which is sum. So sum equals 0. We do this loop that we had over here, I believe. For each subpacket, sum plus equals eval the packet, return sum. Great, that's easy. And then for product, it's exactly the same thing. The only trick with product is remember the identity for products is 1, not 0. Otherwise, you're going to end up with 0 because you're multiplying everything with 0. And it should have at least one packet. Yeah, because it will have at least one literal, right? So we know that this is going to do the right thing in those cases. So we only have 2 more, which is min and max. So which one's min? 2 is min. So min is going to be math.max int64. So these need to actually be int64s, or else it's not going to work. I should put 0 here just to be correct, and that is, okay. Min is going to do that. So do that if, so v is going to be eval p2 if v is less than min, min equals v. Turn min. I'm going to do the same thing here, but for max. Now, I guess the numbers have to be at least 0 because there are no negative numbers in this so far. So if it's greater than max, then it becomes the max, and we return max. And that is every single case, which is great. Should I just do it? Eval packet? No, you know what? No. We won't just do it. We will do our diligence and test this out. Cool. So I just need to get rid of that warning. Let's see. I've got some values that are not mismatched between int64s and ints. This is just something that happens if you use these things. Oh, it's an int. Wow, okay. So we just have to, this one makes sense though. Let's make sure those are okay. Missing return it in the function. Yeah, we are. Return, you know what, let's just log.fatal here. Great, so that's reading the packet. I want to eval the packet. 3. Great. Okay, this will be helpful. So it worked. This is the stuff that I'm really into. That works really well for me. It's just once you have the data structure, parsing the data structure, this is all recursive. You can call eval within eval, and it's all fine. That can be confusing if you haven't worked with recursive data structures before. But because it's a packet, right? It's every subpacket is its own packet, and so you can always eval it all the way down to the bottom. In the best cases, when it's literal, and it will all flow back up. It's really cool. Let's just try the next one. Right, and it's cool that you can see the structure here, right? You can see that it's type ID 1, which means it's a product, and the first one's a 6, the second one's a 9, which so you get 54. You kind of get used to reading these things after a while. This finds a minimum of 7, 8, and 9. It should give me 7. Good. This finds a minimum of the maximum of 7, 8, and 9. So it should give us a 9. Great. This produces 1 because 5 is less than 15. 5 and 15. 5 is less than 15, so it's a 1. This produces 0 because 5 is not greater than 15. 5, 15. Yeah. This produces 0 because 5 doesn't equal 15. Yeah, great. And this produces 1 because 1 plus 3 equals 2 times 2. So this is the first kind of tricky case. Right, you have, here you have a 1 plus 3. Here you have a 2 times 2. And this is the equals check with the 7. So 1 plus 3 is 4, 2 times 2 is 4, and you end up with 1. So let's run this on our data. And we get, this is the result of evaluating my big input. So we just chuck that in, and it's going to be right. So yeah, great challenge. I love these ones. A couple of years ago, Advent of Code did this whole like bytecode um, interpreter sort of thing, and you had to like write programs in it, and you had to debug it. Playing like Breakout or something, I think it was, and you had to work out like what the final score was when you played Breakout. I think it's, for me, who as someone who really likes this kind of programming, it's really fun, and I had a lot of fun. Um, but I think that this type of programming isn't for everyone. I can understand if people don't find this interesting. You might be asking, why do I find this interesting? I don't know, I just do. It tickles that part of my brain that um, works well. And so, yeah, this kind of programming is stuff that I really like and I'm really into. And yeah, you can kind of see I'm so used to this kind of thing that I could read my output with no help, just from knowing the problem description, which is not for everyone. It'll be interesting if something like this comes up again in the future. Advent of Code is known to do multi-day challenges. Like in maybe 3 days, something that reuses this code might come up, and they might introduce some new operator types or whatever. So this is actually a good point in time to kind of package this code up nicely and to put it into some kind of set of helper functions or whatever, so that you can reuse it later on if you need to. Um, but yeah, I don't really have much more to say about today's challenge. It's been almost an hour. Can't believe it took that long. When it's yes, so this stream or this recording is longer than yesterday's recording. But I had so much fun doing today's one, and yesterday's one was so painful. Um, yeah, I didn't even realize time flew by so fast. So yeah, let me know how you got on. Have a great rest of your day wherever you are in the world, and I will see you again tomorrow. Thanks for joining me.